So it's time to come back and add our fifth vector operation. So adding vectors, subtracting vectors, multiplying a vector by a scalar, these we added early on. Since then, we've come back and added how to multiply two vectors together that gives us back a scalar using the dot product. Now we want to add our fifth operation, which is multiplying two vectors together that gives us back a vector using the cross product. So what we're going to see is that the cross product, which is also known as the vector product, is a way of multiplying two vectors together that gives us back a vector. So there's going to be a lot of similarities between the dot product and the cross product. The biggest difference between them is that the dot product gives us back a scalar, the cross product gives us back a vector, which means what we do with the cross product has got to give us back information that contains both magnitude and direction. So let's start with our algebraic rule, and initially let's just think about our vectors being two-dimensional. So what I have are two vectors, vectors A and B, that both lie in the xy plane. X component I hat plus y component j hat for both vector A and vector B. And so my rule for their cross product, so A cross B, so again you'll notice that this sort of large X tells me that I'm taking the cross product between these two vectors. So A cross B, if they both lie only in the xy plane, can be written as the x component of A times the y component of B minus the y component of A times the x component of B. All that times k hat. So again, I've got to get back a vector, and in this case what I see is that my vector points in the z direction. So just to be clear, and in terms of sort of where kind of this cross product label comes from, right, I can make myself a little table that shows the x and y components for my two vectors. And what I'm going to do is I'm going to multiply ax times by, then I'm going to subtract ay times bx. And so you can see here's where sort of the cross comes in my cross product. This is going to give me the value of the cross product, and then again that's going to be the z component, so in the k hat direction. If I have three-dimensional vectors, so now we have some z component for both vector A and vector B. Well, notice that I have the same piece over here for the z component of the cross product that I did when AZ and BZ were both 0. What I've added basically is I have two other very similar looking rules to get the x and y components of the cross product. That the x component of my cross product depends on the difference of products using the y and z components of my initial vectors. And the y component of the cross product depends on the difference of the products between the x and z components. The component of my cross product is going to use the other two components of the vectors A and B. So here's just the rule for calculating out what the cross product is between two three-dimensional vectors. The more important detail is understanding that this cross product is perpendicular to the plane that's defined by my initial two vectors A and B. So what we're going to have is A and B define a plane. So this is similar to, reaching all the way back to high school geometry. You knew that 2 points defined a line. So if you had a point in space, a second point in space, you could always draw some line that connected those 2 points. In a similar way, if you have two vectors that don't lie along the same line, so this is a way of saying that our two vectors can't be collinear. But if we have two non-collinear vectors, so vector A is going to point off in some direction, vector B points in a different direction, those two vectors define a plane. Right? We can draw a plane that runs through both of those two vectors, and then the cross product is always going to be perpendicular to that plane. So if you think back about the two-dimensional vectors, right? So we had our vectors just had x and y components, and their cross product pointed in the z direction. So again, that's telling us that our two vectors lied within the xy plane, and their cross product was perpendicular to that plane by pointing in the z direction. Now we can think about something like the geometric rule that we talked about with dot products, and that's going to give us the magnitude. So it won't give us all the information about a cross product, but it will tell us the magnitude. And so I can think about the magnitude of my cross product as being the magnitude of vector A times the magnitude of vector B times the sine of the angle phi. And again, the angle phi is defined to be the angle between my two vectors A and B. And so one of the things that we want to emphasize here is that phi should never be greater than 180, right? We always want to define the angle phi, draw in the angle phi as the shortest distance between my two vectors A and B. But once I do that, I can then think about how this sine term partners up with either of these two magnitudes. And so let's start with letting sine phi go with the magnitude of B. Well, of course, if this is my angle phi, the magnitude of B times sine phi is nothing more than this component over here on the right that is perpendicular to the vector A, which means that I can rewrite this as the magnitude of A times the component of B that is perpendicular to the line of A. On the other hand, if I take that sine and now partner it up with the A, so A sine phi, again, if here's my angle phi, sine phi is this opposite term, or this opposite side within my right triangle, so A sine phi is again this perpendicular component of A. It's perpendicular to the line of B. And so what you can see is that in each of these cases, what the cross product is telling me about is how much my two vectors are perpendicular to each other. So we said that the dot product tells us about how much our two vectors lie along the same line. The cross product tells us about how much our two vectors are perpendicular to each other. So again, in terms of thinking about this geometric rule, let's take two vectors A and B. And again, there's a couple different ways that we can sort of think about this picture. So let me draw in a coordinate system. And so for starters, let's deal with the situation where vector A points in the positive y direction and vector B points in negative x. So what you'll notice, of course, is that these two vectors clearly lie in the xy plane. The angle phi between them, right, if one of them is along the y-axis, the other one's along the x-axis, then the angle phi here has to be 90 degrees. And so the first thing I know is that the direction of the cross product of two vectors is perpendicular to the plane defined by both vectors. Well, here, my vectors A and B lie within the xy plane, which means that their cross product has to lie along the z-axis. And in this case, A cross B points in the positive z direction. We could use the algebraic rule to calculate this out to see that A cross B points in the positive z direction rather than the negative z direction. We'll also learn a right-hand rule that will help us figure out that A cross B in this case points in positive z rather than negative z. So that's the direction of our cross product. Again, the magnitude is going to be equal to the area of the parallelogram defined by my two vectors. And in this case, that parallelogram is simply a rectangle in the xy plane. Phi here is 90 degrees. Sine of 90 degrees is 1. And so this is just length of A times length of B. It's a rectangle in the xy plane that's going to give me the magnitude of this cross product. So this would be magnitude of A times magnitude of B, and it points in the positive z direction. So let's take those same two vectors, but let's pick a different coordinate system. So basically what we're doing is we're saying now, instead of that being sort of a three-dimensional picture, we're looking down on a two-dimensional picture. So vector A now points in the x direction, vector y points straight up. So this is sort of the two-dimensional picture that we've been dealing with all semester long. And so in this case, again, I want to start by thinking about direction. I know that the direction of my cross product has to be perpendicular to the plane defined by both my vectors. Here, both vectors still lie in the xy plane, which means that their cross product has to point in the z direction. And again, here it points in the positive z direction. It's just that positive z is out of the page. And so one of the things that we're going to add is we need a way to designate whether we have a vector that's coming out towards us or a vector that's going into the page away from us. And so we're going to use these two symbols. So whether this outer circle is there or not is sometimes it'll be there, sometimes it won't. But if you have a dot, that's a vector that points out towards us. This is like we're seeing, again, vectors we represent with arrows. This dot is the point of the arrow that's coming out towards us. This x is going to be the symbol we use to show vectors that are pointing into the page away from us. And again, you can think of this as, hey, this is the back end of the arrow that's pointing away from us. So we're going to use these two symbols to draw vectors that are pointing either out of the page or into the page when we're drawing things in the xy plane. Cross product gives me a vector. The direction points out of the page. My right-hand rule is going to confirm that. We'll learn about the right-hand rule in the next video. So don't worry if that doesn't make sense why we know this is out of the page yet. That's going to come in the next video. Just trust for a moment that A cross B here does point out of the page. And again, the important detail is that that is perpendicular to the plane defined by these two vectors. So they still lie in the xy plane, even though one of them is in x and the other one is just somewhere out here in the first quadrant. So they're not lying along the x and y axes this time, but they still define the xy plane. In terms of magnitude, again, I know that the magnitude of my cross product is going to be equal to the parallelogram defined by my two vectors, vectors a and b. And so again, here's the parallelogram now. Notice it's not a rectangle anymore, right? And so the b sine phi is again telling me that I want this length of a, and now I'm going to multiply it by what is basically the height of this parallelogram that's given by the distance along b that is perpendicular to the line of a. So a couple special cases that we'll deal with. Again, we said that when our two vectors lie along the same line, they're collinear. They're what are known as collinear vectors. And in that case, their cross product is 0. So one way to think about this is if they point in the same direction, the angle between them is 0, sine of 0 is 0, so their cross product, its magnitude is 0. If my two vectors are perpendicular to each other, so now the angle between them is 90 degrees, sine of 90 degrees is 1, so this is the situation where I have the largest magnitude of the cross product. So the more my two vectors are perpendicular to each other, the larger the cross product becomes in terms of its magnitude. And so just restating that, the cross product is at a maximum when the two vectors are perpendicular to each other. If the two vectors point in opposite directions, so now again we're back to the fact that our two vectors are collinear here. The angle between them is 180 degrees. Sine of 180 degrees is again 0, so the magnitude of my cross product is 0. So again, my cross product is 0 when my two vectors are collinear. So it doesn't matter whether they're lie along the same line pointing in the same direction or lie along the same line pointing in the opposite directions. Collinear vectors have 0 cross product because the cross product is trying to tell me about how much my two vectors are perpendicular to each other, which is why I get the maximum magnitude for my cross product when they are perpendicular.